All right, thank you everyone for joining the Ice Giant System seminar series. If this is your first time, the series showcases recent developments in scientific topics covering all aspects of ice giant systems: atmospheres, satellites, rings, magnetic fields, interior structures, as well as science related to formation and evolution. I wanted to put out a reminder to join the listserv. I'll go ahead and drop the link to our website in the chat, and you can go there for all of the recordings of past presentations, as well as sign up for the listserv to get information on upcoming events. So today we have Dr. Raluca Rufu presenting today. So I'll give an introduction to her. She'll give her presentation, and then we'll have some time for discussion afterward, as well as some updates on community news. So Dr. Raluca Rufu obtained her bachelor's degree in physics and planetary sciences from Tel Aviv University and her PhD in planetary science from Weizmann Institute of Science. Since graduation, Raluca has been a postdoctoral researcher at Southwest Research Institute, where she works with Dr. Robin Canup. In 2021, she received the Sagan Fellowship to work on formation of compact exoplanetary systems. Raluca's research to date has focused on the origin of satellites and satellite systems, including our moon, Uranus, and Neptune, and on determining how these objects can constrain planet formation and early dynamical evolution. And today she's going to talk to us about the formation of the Uranian Satellite System. So take it away.
Thank you. Thank you for the introduction and for the invitation to give this seminar. So in this presentation, I'll talk about the formation of the Uranian Satellite System. But first, I wanted to start with a bit of motivation of why studying the formation of the Uranian Satellite System. So an important question in planetary science is, how did the icy giants form? And this is not a very easy problem to solve, because it's not obvious how Uranus and Neptune have acquired some hydrogen and helium atmosphere and did not transform into a giant planet as Saturn and Jupiter. So one way to form these icy giants is by gradual accretion of small bodies. So in a similar way as Jupiter and Saturn, but maybe the circumplanetary disk had a different structure. And a different way is to have a late stage giant impact phase. And this would be more similar to the formation of the terrestrial planets. So in this theory, a few super Earth-sized masses, planetesimals, started to impact each other and eventually create Uranus and Neptune. And one way to answer this question is to look at the satellite system, because the satellite system contains the hints about what happened at the late accretion of these planets. And importantly, Uranus is the only satellite system that we can really test, because the Neptunian system has been disrupted by the arrival of Triton. So Uranus is basically the only satellite system that we can test in order to see how both of these icy giants may have formed. So when we talk about satellite origin, specifically formation of regular satellites, meaning the ones that are prograde and somewhat close to the planet, we talk about two different mechanisms. One is giant impacts, and the second is co-accretion. So first, I'll start with what is a giant impact. So as you can see here in this movie, you have a planetesimal. It's going to impact the target. It's going to eject material into circumplanetary orbits, and it's going to form a debris disk. And that debris disk is going to be composed of a mixture of the outer envelope of the planet and the outer envelope of the impactor. And once the debris disk settles, which is going to take longer than the simulated time here, eventually the debris disk is going to extend up to the Roche radius of the planet. So just a few planetary radii. And eventually this debris disk is going to start viscously spread through the Roche limit and start to accrete satellites. And this is how the formation of our moon probably have occurred, Pluto and Charon, and Phobos and Deimos. So the moons in this theory are going to start very close to the planet, and then they were going to tidally migrate, probably outward in certain conditions. And an important aspect of impacts that I kind of want to introduce is the angular momentum, because these impacts introduce a lot of angular momentum to the target, the rotation, but also to the debris disk. So for the Earth-Moon system, if we take a Mars-sized impactor at an impact angle about 40 degrees with a velocity of around escape velocity from Earth, you would get the angular momentum of the current Earth-Moon system. And this is the canonical giant impact. And hydrodynamic simulations have showed that there is minimal escaping material. So this is what we would call an accreting impact, because most of the angular momentum, most of the mass is retained in this Earth and disk system. But the angular momentum could be even higher, but not necessarily retained inside the system. For example, if you increase the angle or you increase the velocity, then you can get significant material that escapes the system. And this not necessarily is going to create a debris disk that is larger, because a lot of the angular momentum is going to escape from the system. And this is what you usually refer to as a hit and run impact. And this is going to be relevant when we talk about impacts onto Uranus. So the second formation mechanism is formation of satellites by co-accretion, and this is usually the formation that we think of the Galilean satellite system. So during Jupiter's accretion, when the solar nebula was still present, it started to open up a gap, and this is what you see here in this figure. And infalling material from circumstellar orbits are going to fall onto the planet. But because these have too much angular momentum to be accreted directly onto the planet, it flows and forms this circumplanetary disk. And in this circumplanetary disk, this is where the satellite systems are going to be formed. So I'm going to specifically talk about the gas start disk model, which was proposed by Knopp and Ward in 2002 and 2006. But there are other ways to do a similar thing. So in this theory, you have gas and solids that are going to fall onto the circumplanetary disk. Once the dust is in orbit, it's going to start to collide with other dust particles and starts to grow satellites. However, the satellites, when they reach a certain size, they're also going to migrate inward due to type 1 migration, but also due to gas drag, but mostly type 1 migration. So satellites start to accrete, and therefore they're going to have a net force inward and migrate inward. So you're going to lose some of these satellites, but because the infall is continuous, more dusty material is added to the disk, and therefore new satellites can accrete. So there are generation of satellites that accrete and migrate inward. And there's this balance between how fast you can accrete and how fast you migrate inward. And this balance is important because this balance, the satellite growth, which is regulated by how much dusty material you have inside the disk, and this is balanced against the migration loss, so how fast you lose planets. This balance gives a constant total satellite system mass. Because you cannot reach a bigger size because the migration rate is going to be higher and you're going to lose that satellite faster. So you can see kind of this evolution in this movie from Knopp and Ward in 2006. You can see that satellites start to accrete. They would reach this critical size and then migrate slowly at first and then faster and faster. But other satellites are going to form to replace these, and they're going to migrate inward as well. And on the right, you can see the total satellite system mass. You can see that it's going to oscillate around a constant value. You can see sometimes you lose these satellites, so the total satellite system mass is going to decrease, but eventually going to accrete other satellites to replace those. And this constant total satellite system mass is important, and you can show analytically that there is a common mass ratio of 10 to the minus 4 for satellites that have been accreted in this way. And this mass ratio is only weakly dependent on the viscosity of the disk or the inflow. And this is important because this tells us that even though Jupiter and Saturn have accreted in different times and different locations in the solar nebula, they will still have the 10 to the minus 4 mass ratio of the satellite system. And this is consistent with the observations. And just to tie everything up, eventually the solar nebula is going to disperse and the last generation of satellites is going to form. So this is a simulation with just an exponentially decreasing gas disk and inflow. And you can see you have about 2 generations of these satellites until you get something that kind of resembles the Galilean satellite system. So the characteristics of these satellites is that the satellites accrete slowly. It takes about 100,000 years to accrete. And therefore, this allows for low temperatures that are consistent with the ice rock composition of the satellites. The inner satellites are more likely to be rock rich, and this is because the inner satellite is going to migrate inward and feel temperatures that are hotter closer to the planet, but also the inner satellite is usually going to be the older satellite, and therefore it may have been accreted when the infall was increased and the temperature was also higher. There is this common mass ratio of 10 to the minus 4, and this is going to be expected in all of the satellite systems that have been accreted this way. And multi-satellite systems and single satellite systems can result, but multi-satellite systems are more common. So the Saturn system, where most of the mass is inside Titan, is less common, but still possible to create. But the most common outcome would be something that resembles the Galilean satellite system. Okay, so let's talk about the Uranian satellite system and why is it so interesting and so remarkable. So any satellite formation or formation theory needs to explain a few things. And one of these things is the angular momentum of the system. This is kind of obvious because this is what we also do for the moon. But also it has to explain why Uranus has this high obliquity of 98 degrees. Basically, Uranus is a retrograde rotator. This tilt could have happened either by a giant impact or maybe a secular spin orbit resonance. But it also has to explain the architecture and composition of the systems. And you can see that Uranus is somewhat similar, looks somewhat similar as the Galilean satellite system. And the composition itself is a 50-50 rock ice composition, while Miranda, which is the inner satellite, is very icy. So let's just look at what we know about the Uranian system and see whether this fits the impact scenario or the co-accretion scenario. So first, the total mass of the satellite system is 10 to the minus 4 times the planetary mass. And this, for me, is the smoking gun that shows that the satellite system has formed by co-accretion. However, Uranus is a retrograde rotator, and if Uranus has had this tilt when the solar nebula was present, the infalling material onto Uranus would have created a retrograde disk compared to Uranus's rotation, and therefore would have created a satellite system that is retrograde with respect to Uranus. And this is in contrast with what we see today. So the fact that the satellites are prograde with respect to Uranus's rotation and their inclinations are relatively small, this might be a sign that maybe this was an impact. And the impact can tilt the planet and create a debris disk that is going to lie in the new equatorial plane of the planet. However, the satellite systems are somewhat extended. The semi-major axis of Oberon is around 23 Uranian radii, and this is not something you can easily explain by tidal migration alone. So if you start with impact-generated debris disk, the satellites will start very close to the planet and then hopefully migrate outward. But the extent that we currently see cannot be explained with tidal migration alone, and you need something else to explain why the satellite system is so extended. And there was a proposal by Ida et al. In 2020 that maybe the impact-generated debris disk firstly viscously spread outward and only then started to accrete satellites. And this is maybe a reason of why the satellites are so extended. So that's why I put this impact in a question mark of it's not clear whether it is consistent with an impact or not. The four major satellites have a 50-50 rock ice composition. And this is not consistent with an impact because the impact generated debris disk is going to be composed out of the outer envelope of the planet and impactor. So we expect these debris disks to be mostly icy. So there you need a way to explain how most of the rock was retained while some of the ice was not. And the 50-50 rock ice composition, this is something that we would have expected with co-accretion. But to make things even more confusing is Miranda has an icy rich composition. And this is not consistent with co-accretion either, because we expect the inner satellite to be a rock of rocky composition. So co-accretion alone cannot explain the composition of Miranda either. So as you can see, none of the regular things that work beautifully for other systems can really work for the Uranian Satellite System. And I think this is why it's so exciting to study this system, is because everything that we try to throw at it, just something doesn't adds up. So instead, it was proposed that maybe the formation of the Uranian system was due to a co-accretion and a giant impact. And it was proposed by Morbidelli et al. In 2012. So in this theory, you form the satellite system, you form a primordial satellite system by co-accretion. So the architecture would be very similar to the Galilean system, but it has to have formed around an oblique planet. And that obliquity would be similar to what we see for Neptune. And then you have a giant impact that tilts the planet and forms a debris disk, an icy debris disk. This impact also destabilizes the primordial satellite system into crossing orbits, and they would start to collide and grind each other and form this cloud of outer debris. So there are two distinct debris disks that can be a bit confusing. So you have the inner disk, the inner debris disk, or inner C disk is usually referred to. This is the impact generated debris disk. Composition would be mostly icy. And you have the outer disk, which is the orange cloud here. And this orange cloud has the material of the primordial system, would have a 50-50 ice composition. And in certain conditions that I'm going to talk in a few slides, in certain conditions, this cloud that was initially inclined to the new equatorial plane is going to realign and form a symmetric torus around the new equatorial plane. And eventually, collisions between the cloud are going to reaccrete the satellite system on the new equatorial plane of the planet. So if we assume that the efficiency of that accretion is high, you would still maintain the 50-50 rock ice composition and the mass ratio of the initial primordial system. So in this way, you can explain the composition and the mass ratio of the Uranian system, but you can also explain the tilt and why the satellites are prograde with respect to Uranus's rotation. And the inner sea disk, you have to, most of it has to fall onto the planet, but maybe a remnant of this disk is what created Miranda, and that is why Miranda has icy composition. So there are a few things in this theory that were tested. I'm mostly going to focus on the impact itself, but also my colleague Salman and Kanap have tested the reaccretion. I have some backup slides if there's any questions about that, so I hope I could answer regarding that. So if we want to talk about what would tilt the planet, but also cause the realignment of a prograde satellite system into the new equatorial plane, we have to put a few constraints. And the first constraint is that the angle between the initial rotation of the planet and the final rotation of the planet after the impact has to be smaller than 90 degrees. And this means that Uranus was not tilted from 0 to 98 degrees in one impact. So you have to have an initial obliquity of a few tens of degrees. This would be similar to Neptune, and you could create this obliquity either by a previous impact or maybe by spin orbit resonances. The maximum impact velocity of a heliocentric orbit will be only slightly larger than the escape velocity from Uranus. So most of these impacts are going to be accretionary impacts. So most of the angular momentum and most of the mass is going to be retained inside the system. And lastly, in order to realign the outer debris disk, we need to increase the effective J2 of the planet. And you can do this if you have an inner debris disk that has a mass of 10 to the minus 2 uranium mass. And let me just explain a bit more about this constraint. So let's first assume you only have Uranus that has a certain obliquity, so it's a certain J2, and you have an inclined disk. When you're close to the planet, the material on the disk is going to precess around the new equatorial plane of the planet. And the ascending nodes are going to randomize and basically form a symmetric torus. But when the distance is larger, the J2 is not the only one that controls the precession of the material, but also the self-gravity of the disk or the sun can also be influential. And the sun would want to cause the precession of the disk to be around the ecliptic. And while the self-gravity of the disk will want the precession to be around the inclined disk. So as you distance yourself from the planet, that randomization of the nodes is not going to occur, and the disk will retain its inclined shape. And this is what you can kind of see in this right figure. On the left, you can see a figure from Morbidelli et al. In 2012 that you can see that close to the planet, the nodes, the ascending nodes have randomized. So you expect those to basically realign to the new equatorial plane. But once you are more distant to let's say the semi-major axis of Oberon, which is here the vertical line, you can see that the disk will retain its own inclined orbit. So if we reaccrete onto this plane, you would get satellites that are inclined. However, if you add equatorial debris disk, you basically increase the J2 of the planet. And with a larger J2, you can cause this nodal randomization to work for larger distances. So for a mass of 10 to the minus 2, you can randomize the nodes up to Oberon's semi-major axis. So this is where the constraint on how massive the impact-generated debris disk should be. So we performed impact simulations, impact hydrodynamic simulations, but these impacts are computationally very expensive. So we didn't want to do a large phase space that is going to give us a lot of options. We wanted to only constrain ourselves to systems that we know are going to give us the right angular momentum and also the right tilt. We had to restrict the tilt to 90 degrees. So for example, if we assume an initial rotation for the planet and initial obliquity for any initial orientation, and this is what you have here in the x-axis, the initial orientation of the rotation. For a one Earth mass impactor, the impact angles that are going to give you the right angular momentum and the right tilt, the maximum tilt, are going to be oblique impacts. So these are between 20 up to, let's say, 50-degree impact angle. But if you increase the mass of the impactor to, let's say, 3 Earth masses, because it has so much angular momentum, you are only restricted to very head-on impacts. So between, let's say, 5 to 15. And if you impact the planet with a larger impact, you're going to give it too much angular momentum, and the angular momentum, the final angular momentum is not going to be consistent with the current system, or you're going to tilt the planet to more than 90 degrees that we don't want. So this is one of these simulations. We used SPH simulations, so smooth particle hydrodynamics. Here the colors will represent the temperature, and this impact specific is with 0.8 Earth masses at a 1 escape velocity. And at the bottom, you can see the results from this impact. You can see that the angular momentum and the mass of the planet is consistent with the current system, so it's very close to 1. But if we look at the disk mass that was created, and this disk mass is calculated by taking each particle and calculating its angular momentum and trying to figure out whether the angular momentum is enough in order to be sustained above the planetary radii. And you can see that the calculated disk mass is 2 orders of magnitude lower than what we would want in order to randomize the nodes up to Oberon's semi-major axis. And this is kind of consistent with what we saw in most of our simulations. So this figure is going to kind of summarize these impact simulation. On the x-axis, you have the disk mass. On the y-axis, you have the disk mass, and the x-axis is the impact parameter, so just the impact angle. And the color of the markers represent the final angular momentum of the system. So you would want to have this orange color, because this orange color would mean it's consistent with the current system. And in order to be successful, you want to have a mass that is larger than 10 to the minus 2. And this is the requirement in order to realign the outer disk, the outer primordial disk, to Oberon's semi-major axis. And you can see with 1 Earth masses, you cannot really, you get 2 orders of magnitude less than you would need. With larger impactors for three Earth masses, you are strictly restricted to this head-on impacts that are, we know they're not good in creating a lot of debris disk, because there's not a lot of angular momentum to cause the ejection and to sustain these particles in orbit. If you decrease the impactor mass, you can somewhat get a larger debris disk, but still this is kind of, let's say, order of magnitude less than what we would require. So we conclude that there's no sufficient inner disk mass in order to reorient the satellite system after the impact. So to conclude, the formation by co-accretion and giant impact seems to be a very promising mechanism, because it can explain the mass ratio, the 10 to the -4, can explain the composition, why it's so similar to the Galilean system. And it also can explain why the planet is tilted and how come the satellites are orbiting in a prograde, low-inclined orbits. However, when we started to study this, we didn't find any favorable region in the probable impact phase space that can form inner disk masses of 10 to the -2 uranium mass that are required in order to realign the outer disk, and are also consistent with angular momentum values that are comparable with the current system. So what are the other possibilities? So the other possibilities that we proposed in the paper is maybe there is a modified version of the co-accretion and giant impact. And this relies on the fact that maybe the satellite system was not as extended as we currently see it. Maybe it was more compact and therefore would require a smaller impact generated debris disk in order to realign it. And then you have to explain, well, how do you explain the current orbits? So maybe there was some viscous spreading that occurred after the realignment. Maybe the Uranian system had formed by co-accretion, but the tilt itself was acquired via spin orbit resonance. And this can work. However, it's hard to explain how you would reach the 98-degree obliquity. And sometimes you still need a few giant impacts, 1 or 2, to explain the full 98-degree. It was also proposed that maybe there is a spin orbit resonance with a previous satellite, or maybe with Planet 9. But it's really hard to understand if this could be true and this could work, because we don't have a lot of data of something that we don't see. And maybe the satellite system was indeed formed by an impact and then a vigorous viscous spreading of the disk after the impact and before the accretion started. This was proposed by Ida et al. In 2020. But in order to cause this vigorous viscous spreading, you need to start with an initial debris disk that is significantly large, around 10 to the -2. And from our simulation, we see that it's very hard to reach these debris disks that are consistent with the current angular momentum of the system. So I just want to end with a few kind of open questions of what would be great if we would know better. And this is something that is going to motivate any orbiter or any space exploration that can reach these systems. So we really need to know what are the ages of these major moons. We only have one hemisphere, most of it with very low resolution. We need to know what is the crater distribution and to infer a range from these moons, because this is going to constrain our theories of satellite formation. We need more accurate densities and more accurate shapes. As I said, Miranda seems to be icy rich, but the densities are not well constrained. So maybe some rock or some porosity is still consistent. we need to know what is the tidal migration rate, and to understand whether a migration rate that is higher than what we usually think is consistent with the system, because we see these things happening in the Saturn system and the Jupiter system, and maybe these are possible in the Uranian system as well. And importantly, we need to know the thermal state of these major moons and the question of whether they're differentiated or not. Because if they're not differentiated, this is going to be very hard to explain with a giant impact. And I'll end here and answer any questions that I can. Thank you.
Thank you so much, Raluca. That was a really interesting talk. If you have questions for her, feel free to drop it in the chat or raise your hand. Let's see what we have so far. Okay, Jessica Noviello says, to what level of precision do we need the ages? Is it enough to get age estimates from crater counting, or do we need a sample return?
I think a sample return is going to be a long shot. We can't do it for Mars. So let's just say estimation from the crater density.
While people are thinking about their questions, I have a question.
Yeah.
So you talked a lot about the possible scenarios for formation and Uranus's current configuration. Can you talk at all about why some of these scenarios might have occurred at Uranus versus Neptune or some of the gas giants? What is different about this system in particular?
Right. So Neptune and Uranus are annoyingly very similar and different at the same time. So if we look at the angular momentum or the rotations of these planets, the rotation seems to be similar. So you cannot invoke too many impacts or a substantial impact onto Uranus without Neptune, because then the rotations would not match. The obliquity itself, we see a large obliquity on Uranus, but we don't see it on Neptune. And we can easily explain the Neptune obliquity with spin orbit resonances, while this is not enough for Uranus. So maybe there was some stochastic formation where Uranus may have had one giant impact that Neptune did not have. And some of Neptune's data might be consistent with a giant impact, maybe at a different angle compared to Uranus. So it seems that these systems may have had some giant impact phase, but maybe it was not as substantial as previously thought, when maybe these are super Earths that started to impact each other, because then it's hard to explain how you form two.
Okay, let's see, we have another question. How do Uranus's rings play into the story?
This is a good question. So the rings, it really depends on the, maybe the rings could be a remnant of the impact generated debris disk, or maybe the rings could be formed after the satellite system has already formed. So maybe there was some disruption that occurred in the system, and this is what created the rings. And we really need to understand the ages of the rings in order to answer this question that I don't think there's any good estimate on the ages.
Okay. Well, feel free to continue to drop questions in the chat or raise your hand. Oh no, not another ring age controversy. Yeah, feel free to continue thinking of your questions, I'm going to go ahead and share my screen to share some community news. Let's see here. I can never figure out how to get this to work when I want it to work. We'll just do it this way. Okay, so, and I'll drop all of these in the chat here. So our next Ice Giants seminar series will be on January 9th at 11 a.m. Eastern, featuring Henry Garrett and Insu Jun at JPL. We have some updates on job postings. We have a Lowell postdoctoral fellowship, which the deadline is tomorrow. So if you know of people that are interested in that, share that as widely as you can soon. There are some positions. There's a Ring Moon PDS astronomer and archivist position. NAU is looking for a remote sensing faculty position. I believe it's actually a cluster hire. We have an OPAG meeting coming up at the end of November, which is exciting. Oh, we have a question from Henry Garrett. Is there a role for the weird Uranian magnetic field?
It could be, there could be a role, and that will depend maybe on the structure of Uranus, something that maybe we could see whether it was heavily influenced by a giant impact or not, but I don't have any other insight other than that.
And we have another question. You noted that there might be multiple impacts on Uranus. Would it be more than 2 or 3?
It seems that it's either 1 or 2. From in order to explain this, the tilt and the spin.
Okay. So that's all the community news, and I'll just put up a plug here for the Uranus flagship workshop coming up in May. The indication of interest form is open, so if you'd like updates on that, feel free to fill that out, and I'll drop in this link that has the information here. All right, unless there are any other burning questions, thank you so much, Raluca, for this wonderful presentation. We really appreciate it. Thank you for agreeing to give this talk. I hope to see you all in January. Take care.
Bye.